Okay, the function f is given by that, x greater than 0. Show the derivative is that. Okay, so we are going to do quotient rule. So we're going to have x squared on the bottom, v on the bottom, and we start with v as well, times the derivative of natural log, which is 1 over 2x, and then times the derivative 2, the derivative of the inside, and then subtract the derivative of v, which is 1, times u. So then this is just going, the 2's cancel and the x's cancel, so that's just 1 minus natural log 2x over x squared. Hence, prove that the graph of f can only have one local max or min point. So we would set this equal to 0, multiplied by x squared, and then we're going to have natural log 2x. And if we write this exponentially, we're going to have e to the 1 equals 2x. So x is e over 2. So then we're going to have, to find the maximum point, so they tell us it's a maximum, we will substitute this back into the original function. So we have natural log 2 e over 2 over e over 2. So the 2's cancel. Natural log e is just 1 over e over 2. So this is 2 over e. So the coordinate point is e over 2, 2 over e. Now, by showing that the second derivative is that, or otherwise, find the coordinates of the inflection. So this is the derivative. So we're going to have, we're going to have, okay, the second derivative, we're going to have, starting with v squared, so x squared squared, and starting with v up top, and then we're going to have v times the derivative of u, which is going to be negative 1 over 2x times 2, and then minus, when we sub in the derivative of v, which is 2x, and then times 1 minus natural log 2x. And then we are going to have, so one of the x's cancels, the 2 cancels, so we're going to have negative x up top, and then minus 2x when we distribute this, plus 2x natural log 2x over x to the 4th. So we can factor out, well, I'll do that in a second. So that's negative 3x plus 2x natural log 2x over x to the 4th, and we can factor out an x. So it's negative 3 plus 2 natural log 2x over x to the 4th. So then we get what they asked, 2 natural log 2x minus 3 over x cubed when the x cancels. Then we set that equal to 0 to find the inflection point. So 2 natural log 2x minus 3 equals 0. So add 3, divide by 2. And then we can write this exponentially. E to the 3 over 2 equals 2x. So we're going to have x is 1/2 e to the 3 over 2. And then we have to sub that into the original function. and that's going to be natural log 2, and then 1/2 e to the 3 over 2 over 1/2 e to the 3 over 2. So these 2's cancel. So this top bit is going to be 3 over 2 because the natural log, that exponent comes down in front, and then natural log e is 1. And then we have over 1/2 e to the 3 over 2. So we're just going to have 3 over e to the 3 over 2. So that is our point of inflection. We don't have to check that it changes concavity because they tell us it's a point of inflection. All right, 38. We've got this function. By considering first and second derivatives, show there's one min and find the coordinates. Okay, so first derivative, product rule, first times the derivative of the second plus the derivative of the first, which is 1 times the second. And we can pull out an e to the 2x plus 1 on the inside, and second derivative is going to be first times the derivative of the second plus the derivative of the first times the second. And we need to find, so we have it factored. This is the first derivative equal to 0. So e to the 2x is never 0. And then for 2x plus 1, we're going to have x equals negative 1/2. And we need to sub that in to the second derivative to show that this is a minimum. So it's got to be a positive number because that means it's concave up. Okay, so plus 2 e to the 2x, 2 times negative 1/2 plus 1. So this is positive and this is positive because it doesn't matter if e's to a negative number, it's still positive. This is going to be 0. So this is positive, so the second derivative is greater than 0, which means it's concave up. So that means p is a minimum. So now we've got the x coordinate of our minimum. We just have to sub it back into the original function, which is negative 1/2 e to the 2 times negative 1/2, which is negative 1. So negative 1 over 2e. So our point P is this. Now B, show that F has a point of inflection. So now if we have our second derivative, I'm going to factor out an e to the 2 to the x. This should add a 2 there. So yeah, 2e to the 2x, and then we'll have 1 plus 2x plus 1, so it's actually 2x plus 2. So if we want the point of inflection, we set the second derivative equals 0. This is never 0, but here 2x plus 2, we would have x equals negative 1. So that's shown. Determine the intervals on the domain of f, where f is concave up and concave down. So we have that there's a point of inflection at negative 1. So we just have to sub into the second derivative x's on either side. So this is always positive So if we sub in -2, it'll be negative, because that will be negative at -2. And then at 0, we'll have a positive there. So it's concave down from -infinity to -1, and concave up from -1 to infinity. So now, sketch F, clearly showing any intercepts, asymptotes, and the points P and Q. Okay, so x-intercept is 0 because, x-intercept, y-intercept 0, because if x is 0, then the whole thing's 0, and yeah, that's the only 0 we're gonna have. So then we have that there is a minimum at -1/2 (1/2e). So like here, because that's just two negative numbers. And then we have a point of inflection at -1, and we actually need to see f at -1, which is -1e to the -2. Okay, so that is going to be the point of inflection. So -1, which is like here. So we also need the asymptote. So because this is never going, so as x gets really small, so as x gets really small, so if we have like -100, e to the 200, -200. So that is -100 over e to the 200, which is going to be a really small number. So that means that the asymptote, so as x gets really small, it's approaching that. So we're going to have something, that's the minimum. And then as x gets really large, say it's 100, this is going to be huge, okay? So it's going to be something like that. All right, 39. The following diagram shows the graph of that. Points lie on the graph of F. Two of these are points of inflection. That's going to be B and D. Find the derivative. So the derivative of E is itself, and then chain rule. Show that the second derivative is that. So we're going to have the first times the derivative of the second plus the derivative of the first times the second. So now we're going to have -2e to the -x squared plus 4x squared e to the -x squared. And we can, well, they want us to factor out just an e to the -x squared. And then it's going to be 4x squared minus 2. Let me just, so for this one, e to the -x squared, v is -2x, so dv is -2, and du is e to the -x squared times the derivative of -x squared, which is -2x. So that's how I get u times the derivative of v plus the derivative of u times v. Anyways, so find the x-coordinate of each point of inflection. So we're going to have the second derivative equal to 0. E never equals 0, so we're just going to have x squared equals 2 over 4, 1/2. So x is plus or minus root 1 over 2. So that's C. Use the second derivative to show that one of these is a point of inflection. Okay, so we're going to have negative 1 over root 2, and we're going to have 1 over root 2. So this is going, so our test point in the middle is 0, and then if you don't know what 1 over root 2 is, just pick something like 4, something larger. So we'll do negative 4 as well. And that goes into the second derivative. That's always positive. And then we're going to have, when we sub in positive 4, that's going to be a positive. When we sub in 0, that's a negative. This is a point of inflection. And then if we sub in negative 4, we're also going to have a positive. So I think what the question is saying is, like, just show that one of these points is a point of inflection, because they're both points of inflection. I thought what it was asking was, like, only one of these points was a point of inflection, but both of them are. You just only had to sub in 0 and 4, or 0 and negative 4. Okay, 40. We've got this function. Write down the equation of the vertical asymptote. Well, that's at x equals negative 1. The horizontal asymptote, since we have the degree of the numerator is less than the degree of the denominator, we have it at y equals 0. And then 3, we want to sketch the graph. So you need to go to the graphing calculator and get some intercepts and all of that. So here's the here are the asymptotes. So if you get the graph on the graphing calculator, you can get the endpoints. So if we sub in negative 3, for example, we're going to have a pretty small number, because that's going to be 2 over negative 26. So at negative 3, we're going to have a small number, 2 over negative 26. And then if we sub in 3, we're going to have the point, something very small here as well. So 3, and then it's going to be 2 over 28. Okay? Now, if they give us the first derivative in BI, if we set that equal to 0 and cross multiply by the denominator, we're just going to have negative 6x squared equals 0. So we know there is a max-min stationary point at 0. You can see on the graph it's a stationary point. So if we sub it in, we get 2, and that's our y-intercept. And then let's just go ahead and show our second derivative. We're going to have v on the bottom. So 1 plus x cubed squared, which is to the 4th. And then we're going to have 1 plus x cubed squared. So v times the derivative of u, which is negative 12x, minus minus u times the derivative of v, which is 2, 1 plus x cubed to the 1 times 3x squared by chain rule. Okay, so now we can take out a 1 plus x cubed, just one of those, and then we need another one, and we need a negative 12x, and then let's just make that plus, and then we're going to have 6 times 2 times 3, so that's 36, and then x to the 4th. And then that's over 1 plus x cubed to the 4th. And one of those is going to cancel. So this cancels like that. So on the denominator, we're going to have this. And then on the numerator, if we distribute this, we're going to have negative 12x. And then we're going to have minus 12x cubed. No, sorry, minus 12x to the 4th plus 36x to the 4th. So we're going to have plus 24x to the 4th. So, and they want it written like this. So if we factor out a 12x, we're going to have negative 1 plus 2x cubed, and then over that thing. So we have showed BI, and if we set this equal to 0, denominator goes away, so we're going to have x equals 0 as an inflection point, which is this thing, and then we have negative 1 plus 2x cubed is 0, so we're going to have x cubed is 1/2, so we're going to have x is the cubed root of 1 over 2. So that is the other point of inflection there. When you substitute that in to the original function, you're going to have 2 over 1 plus that cubed, which is just going to be 1/2. So 3/2, that's 4/3. Okay, so a cubed root of 1/2, it's going to be 4/3. So like here, so we know this is approaching the asymptote. There is a stationary point. Change in concavity, which I should have probably checked. So if we check 1 and 0 into the second derivative, we're going to have a positive on the bottom. So for 0, we're going to have a positive, and then up top, okay, so we can't plug in 0. If we sub in negative 1, so we're going to have a negative times, oh, you can't do negative 1 either because that's the asymptote. Negative 2 then. Okay, so we're going to have a negative here times a negative as well, so that's a positive. And then on the bottom, it's going to be a negative. And then at 1, we're going to have positive, positive, positive. Okay, so yeah, it's a point of inflection. All right, so you see it's concave down before there, and then it's going to be concave up, and we know it stops there at that 3. Now on the other side, there's nothing going on. It's just like that. Okay? Tough.